Okay, so improper integrals are going to be either integrals to infinity, plus or minus infinity, or it's going to be integrals over discontinuities. And in particular, asymptotes. So either the function is going to go off to infinity asymptotically, and we want to know, can I somehow integrate that or integrate up to that asymptote? Or possibly the function might be decaying out to positive infinity, and I want to know, can we compute that total area? So to be a little more specific, let's take a look at our first example. Is just going to be the integral from 1 to infinity and 1 over x squared dx. So graphically, what's happening, we've got our function, and it starts to get really small out towards infinity. And what do we want? We want to know, well, what's an integral? An integral just represents the area. And in some sense, we really just want to know, is there finite area? I'm integrating all the way out to infinity, and, well, you can kind of imagine that if this decays fast enough, if this approaches 0 fast enough, then the total area under this thing might actually be finite, even though we're spreading out to an infinite length. This is starting to get into concepts of convergent and divergent, which we're going to be spending quite a bit of time on, especially once we start moving into sequences and series. In some sense, what we're going to find later in the semester is, well, if I add up infinitely many numbers, can I get a finite value? And it's thinking about, like, if the numbers that we're adding up get small enough, fast enough, and if they're shrinking really, really fast, I can actually add up infinitely many numbers. And you can kind of think about that in terms of maybe like a Riemann sum for this guy, right? If I break this down into a Riemann sum into some sort of boxes, well, the height of the boxes is decreasing. And the idea is, if it's decreasing fast enough, we actually get a finite value. So let's go ahead and let's write a few things about that down. So if we get a finite value, i.e. the total area is finite, we say that the integral converges. If the area becomes infinite, infinite, or cannot be computed, specifically, it does not exist. So when I specifically say cannot be computed, I don't just mean, it's too hard, I can't compute it. I mean, in some sense, like, it doesn't exist. Like, it's going to oscillate. Like, we're adding up a bunch of positive and negative values, and it's just going to keep changing. We'll see an example of that later. Does not exist. Then excuse me, the integral diverges. So let's take a look. How do we approach these? Approaching these, it isn't too bad. There's really not much more we have to do. We know all the fancy techniques of integration. What we want to do is just put in a dummy value for that infinity. Let's just integrate up to some finite value t. So really all we're doing is saying, well, let's pick some value t. Let's integrate up to that. And then let's take the limit as I just extend t out to infinity and see if it converges or diverges to see if we get a finite value or not. So integrating this, what do we get? We'll have our limit as t goes to infinity. So the integral of 1 over x squared, hopefully everyone is getting familiar with, that's just x to the minus 2. So we should get a negative x to the minus 1. We've got 1 to t as our limits. And when we plug in our limits, we will get, plug in our t, we get negative 1 over t minus negative 1. In other words, we are trying to find the limit as t goes to infinity of 1 minus 1 over t. And now, what happens when I plug in infinity? So 1 over infinity, remember, is just 0. So we get 1. So this integral converges. The other word you might see is whoops, can't spell today, is the word convergent. So of course, converge is just a verb, convergent, the adjective. So the integral of 1 over x squared is a convergent integral. So the other ones we might consider is now, well, that was 1 over x squared. What about 1 over x? So we do the same thing. That infinity is what makes it an improper integral. So we just want to take the limit as t goes to infinity from 1 to t, 1 over x dx. Our antiderivative is now natural log of x. And I forgot my limit there. As t goes to infinity, we plug in everything. Natural log of 1 so natural log of 1 is just 0. But what's going to happen here as t goes to infinity? Natural log is going to go off to infinity itself. So here we get infinity, which means it diverges or is divergent. So nothing too tricky with these, at least the ones to infinity. Just got to remember how to take limits. So sometimes you got to do L'Hopital's rule to take your limits. So let's do something like the integral from minus infinity up to 0 of x e to the x dx. And here we'll have our fancier integration techniques as well. So it's improper because we're integrating out to infinity. It's x e to the x. Unfortunately, there's not a good u sub for that. So next thing we might want to consider is integration by parts. Integration by parts works nicely because we can get rid of that x. So let's make our u our x, our du is just dx, our dv e to the x dx. So our v is e to the x. We plug those in our formula. So our uv minus the integral of v du. And our integral is going to become x e to the x minus the integral of v du. So e to the x dx. I'm going to go ahead and hold off. So the bounds are still there. I'm not going to plug them in, just because this integral is pretty easy. And so let's just go ahead and complete the anti-differentiation. The antiderivative of e to the x, of course, just gives me another e to the x. And then I'm going to evaluate everything minus infinity to 0. So really, we want to treat that minus infinity as a t and then take the limit. So this is going to be the limit as t goes to infinity, negative infinity, excuse me, of, let's say, x e to the x minus e to the x. And then I got my t to 0. We go ahead and plug in the values. So plugging in 0, it's going to kill that first term. We will have a minus, so 0 minus e to the 0, which is just 1. Minus, when I plug in t, we will get t e to the t minus e to the t. We still got our limit as t goes to negative infinity. And so what do we got? We've got limit as t goes to minus infinity of 1 minus t e to the t minus e to the t. And so now we just have to remember how to compute the limit for each of these guys. So just a quick refresher on Calc 1. First step with a lot of these, you want to plug in your limit. So it's going to be 1 minus negative infinity times 0 minus, I guess I should write that. It's e to the minus infinity, right? Minus e to the minus infinity. But e to the minus infinity is just 0. So 1 minus is where I got that negative infinity times 0 minus 0. And it's this guy that's a problem. This is our indeterminate. So the 1 is a constant. I can keep the 1 there. I can keep this 0 there. That's a finite value. It's the indeterminate part that we kind of have to mess with.
Why is it minus et? 1 minus te e to the t minus et instead of plus et?
Did I miss a minus sign somewhere? Here, here. No,
So
I
you
mean, so
distribute
this
you
minus came.
distribute the minus to the negative et. Shouldn't it be a positive?
That one was the one I missed. Thank you. Yeah, so plus e to the t.
Yep.
So minus e to the t. That term ended up being 0. So, yeah, thank you for catching that. Yep. And then so what do we need? We need to deal with this limit. So we were looking at just that piece. So let's pick that guy out. Was this component of the limit that we needed to compute. We saw that we got a minus infinity times 0. This is an indeterminate form. And from Calc 1, hopefully you remembered how to deal with these indeterminate forms. There's a couple of different ways. Anytime you have a 0 times infinity, remember we want to force one of those terms into a denominator. We want to use L'Hopital's rule for essentially all indeterminate forms. And L'Hopital's rule can only be used for 0 over 0 or infinity over infinity. So if you don't even have a fraction, you kind of have to force this. And so what I'm going to do is write this as the limit as t goes to minus infinity of, I'm going to keep that t. Well, we could do this either way. You could keep the t in the numerator and write it as divided by e to the minus t. So notice I didn't actually change anything, right? It's just algebra. We just changed the way it looks. But the nice thing about this is that now when I plug in the minus infinity, we will get negative infinity over, it'll be e to the negative infinity, which will be infinity over infinity. And the reason I actually chose this e to go into the denominator is because exponential functions are nice with derivatives, right? All I have to do is change the sign in the exponential when I want to put it in either a numerator or denominator, whenever I switch that. If I wanted to force this t into a denominator, it would be e to the t divided by the quantity 1 over t. Thinking ahead and now knowing that I have to use L'Hopital's rule, taking a derivative of the top and the derivative of the bottom is a little bit more of a pain with that 1 over t. So I like taking derivatives of polynomials, especially just t, because it'll go away. It'll make the next step computable. So by L'Hopital's rule, we take a derivative of the numerator, which is just 1, and the derivative of the denominator, negative e to the minus t. And both those derivatives were pretty easy. And now when I compute the limit, that numerator is still just 1. And then, of course, we'll have an infinity in the denominator. And so we will get 0 there. So returning that, if we want to, let me squeeze this in on this page if that's not too much for you guys. We want to sort of pull what we did here and what we found. So we plugged in a 1 minus this middle part we found was 0. So our limit, when I plug that in, is just 1 minus 0, and then that was a plus 0. So overall, we get 1 for the whole problem. And that converges. Any questions on that? So you just got to remember how to deal with all of the indeterminate forms, infinity over infinity, 0 over 0. infinity times 0, 1 to the 0, all that kind of stuff. Hopefully, they won't get too complicated with the type of indeterminate forms that show up. Okay, so let's return to these first couple of examples because we want, tomorrow we're going to spend a couple of days talking about improper integrals, and we want to start talking about comparisons. And how can I determine when functions will converge or diverge just by comparing it to another function? We'll get to more of that tomorrow, but we want to start coming up with some general rules, things to look for. So specifically, if I have this integral of 1 to the infinity, we saw that 1 over x diverges, but 1 over x squared will converge. So let's just say we have some exponent there, p. So for p is constant, and of course, not 0. We want to know, well, when will this converge or diverge? What values of p will the integral be convergent or divergent? So this will give us sort of some general understanding of what to look for, especially in these polynomials or rational functions where the denominator is a polynomial. Well, we solve it the same way we did the previous two. We've got the limit as t goes to infinity of 1 to t, 1 over x to the p dx. And now what is this integral going to be? So we've got, this is going to be equal to the limit as t goes to infinity of, so we're going to have to split it into cases now. So if p is 1, we will get natural log of x. This is when p is equal to 1. And if p is not equal to 1, what do we get? So it's x to the minus p. We should get x to the minus p plus 1, or in other words, 1 over x to the p minus 1. And then we need to divide by that. So 1 over, so I'm trying to do this in my head here. Was it minus p plus 1? And of course, we need to evaluate that from 1 to t. So this is x to the minus p plus 1. And of course, when I take a derivative, it will just cancel that constant. And actually, let's go ahead and change that a little bit. Let's make this other caveat. P is non-zero. Let's just say specifically that p is bigger than 0. If p is negative, that's just going to be a polynomial, and we can kind of flip it to the numerator, right? And hopefully, everyone has an idea that if I'm integrating a polynomial out to infinity, it should diverge, right? Because polynomials, if the function itself goes to infinity, then the area under it is going to be infinite. It's really these decaying situations that we want to know. Does a function decay and approach 0 fast enough in order to get some sort of finite area? So this is p not equal to 1. But, of course, just as a note, here, let me put that in parentheses. P can be a fraction. So what do we get? We get our limit as t goes to infinity. We just want to compute both of these cases. Well, in the first case, what are we going to get? We've got natural log of t. And then it was minus 0 when I plug in that. We've got 1 over minus p plus 1 times, let's go ahead and evaluate everything. So we've got 1 over t to the p minus 1 minus 1. And again, these were our cases, p equal to 1 and p not equal to 1. So we're going to have to split this down into cases again. Let me know if the notes are getting a little too complicated. When I plug in this infinity to the t, this one goes to infinity. So this one diverges. Now for p not equal to 1, we actually want to split it into essentially p less than 1 and p strictly bigger than 1. So we have the limit as t goes to infinity of 1 over minus p plus 1 of 1 over t to the p minus 1 minus 1. So what's going to happen? If, let's say p is bigger than 1, then 1 over t to the p minus 1. If p is bigger than 1, then exponent is positive. Meaning that it's positive in the denominator, right? It's that t to the p minus 1 in a denominator, which means what's going to happen when I compute the limit? It will be infinity. It'll be 1 over infinity in the denominator. And so this guy will converge. So I just multiplied the minus signs. This is a negative 1 times that whole quantity, which will flip the signs in the denominator. And it'll converge. So that is our rule here. And that should match what we found in the first problem. We saw that if our denominator, or if the power of the polynomial in the denominator, if it's bigger than 1, it'll converge. So our 1 over x squared converged. However, if it's 1 or less, it'll diverge. So what's going to happen with that? So if p is less than 1, what are we trying to compute? This is the limit as t goes to infinity of this guy again. But this p minus 1 is negative. So in other words, we can write this as the limit as t goes to infinity, 1 over minus p plus 1. I can write it as t to the 1 minus p. So all I did was flip this guy from a denominator to a numerator, which means I multiplied by the exponent by a negative 1. Right? So if p minus 1 is negative, 1 minus p, since p is now less than 1, is positive, meaning when I plug in infinity, what are we going to get? It's just a regular polynomial or a positive powered function. And so we'll get an infinity there. So let's write that down. So here's our rule. Integral from 1 to infinity of 1 over x to the p dx. It will converge if p is strictly bigger than 1, and it will diverge if p is less than or equal to 1. Everyone follow all that? Any questions? So now we know essentially straight up, without computing things, we know that if I'm given things like 1 to infinity, 1 over x cubed, if we're just asked convergent or divergent, we know what's going to happen with these guys. I could say things like, what about the integral of 3 to infinity? 1 over, let's say, x to the 5th. Convergent or divergent? Well, I know that the integral, you can kind of think about it like this way. One to 3. So what's going on with this guy? Well, I changed the bound is all we did, but really the problem was the infinity. So you should have a notion that, well, this will still converge because we're still starting at some finite number up to infinity. And well, how can we show that? Well, I know that this guy converges. Now, if I just change the bound to 1 to infinity, but I started at 3. So if I subtract off the integral from 1 to 3 of this guy, we get the same thing. And of course, this is just a finite integral, which is fine. No problems there. And I know that this guy converges. So since both of these numbers are finite, the whole thing will converge. So really, it actually doesn't even matter what bound this is. as long as it's not 0, right? We haven't learned to deal with discontinuities. This function will be asymptotic at 0. So as long as it's bigger than 0 and we're integrating out to positive infinity, no problems. I know whether it's going to converge or diverge. And that will also hold if it's a divergent. So if I change the bound, even 10 to infinity of 1 over x, and let's say x to the 1/2. So 1 over square root of x still diverges. And why is that? Well, because if I start from 1 to infinity, I know I'm going to have an infinite area under that curve. So if I have an infinite area, even though I'm starting later, I'm only subtracting off a finite amount of values from an infinite area. So like pictorially, what's going on here? 1 over x squared, it kind of decays, but not fast enough. Or excuse me, 1 over square root of x. So I know that if I start from 1, I know that the total area out to infinity is divergent. Is infinity. So if I just subtract off this and start at 10 and go out to infinity, well, this is a finite amount from infinity. I'm still left with infinite area. So it's still going to diverge. Okay, so that's our general rule. That's in a different note sheet. Let's see a couple of examples real quick, just to compute a few more. Then we need to talk about what's going on with discontinuities. So what happens like if I change those bounds now to 0 to 1? And can we deal with those? So let's just take a look at something like the integral of minus infinity to infinity of 1 over 1 plus x squared dx. So this one has 2 infinities. And to technically do it proper, what we would want to do is almost set this up as a double limit. We'll say it limit as t goes to infinity, and the limit as s goes to negative infinity. S to t, 1 over 1 plus x squared dx. Because really, these are 2 independent bounds. I can go at different rates, so to speak, to positive and negative infinity, and we should be able to consider them separately. It's not a huge point. It's kind of just like a technical math formality. You could use t for like a negative t and t. You're going to essentially get the same answer. And well, how do I anti-differentiate this guy? 1 over 1 plus x squared, that just gives me arctan. Sorry. We've got arctan x, and of course I want to evaluate that from s to t. Problem with writing, I don't have an eraser since we're not using chalkboards. And evaluating, so the limit as t goes to infinity, limit as s goes to infinity. We'll have arctan of t minus arctan of s. And now you just have to remember your limits of all your functions of arctan and whatnot. So of course we see some L'Hopital's rule examples. Arctan What does arctan look like? Looks like this. And these bounds are pi over 2 and minus pi over 2. So remember, it's just like tangent, but then flipped over a diagonal. So tangent has asymptotes between minus pi over 2 and pi over 2. So when I take arctan, those become my y asymptotes on the y-axis, perpendicular or parallel to the x-axis. So of course, what's the limit when arctan goes off to infinity? It's going to be pi over 2 minus, when arctan goes to minus infinity, negative pi over 2. And we just get pi. So nothing too tricky with that example. Just got to remember your arctan limits. Some of these other trig functions might be coming up here as well. Just got to remember all the pre-calc and calc skills you've learned. So the last one, at least for this section, that I wanted to do was integral of 0 to infinity for sine of x dx. And this is one of those does not exist limits. What's the integral of sine? So this is just going to be the limit as t goes to infinity. Let's go ahead and do the integral. So the antiderivative is minus cosine x. And I'm just going to stick in that t for the infinity there. So it's, of course, the limit as t goes to infinity of minus cosine t plus 1. So minus a negative cosine of 0 is 1. But now what happens? What's the limit as t goes to infinity of cosine of t? So, of course, our cosine starts here and then goes down, goes up, goes down and up. And, of course, what's going to happen at infinity? That limit does not exist. It's bounded. It doesn't go off to infinity. It's just like cosine is going to keep oscillating and oscillating. So what do we mean by infinity? What value does it get at infinity? Well, it could be anything between minus and 1 and 1. So this one diverges. So that's all you would have to say for that, guy. Since it does not exist, the integral diverges. Any questions on any of those? So nothing too fancy there. Just got to remember your limits to infinity. All the integration techniques still apply. The limits of discontinuities are a little bit trickier because sometimes you got to pick it out. Sometimes it's not clear that it's an improper integral. And these can be the types of things that might show up on an exam where it's like you have to compute an integral. It doesn't look bad because the bounds are fine, but there might be an asymptote or a discontinuity. So you just got to be mindful and watch out for stuff like that. So we'll say improper with discontinuities. So for example, say I have the integral from 2 to 5 of 1 over square root of x minus 2. So you have to just recognize that it's improper because the function has an asymptote. at x equals 2. And we want to integrate up to 2. So essentially what's going on is, let's draw a picture. We've got 1 over square root, so we're going, and so the function looks something like that. So it's kind of similar to the last ones, except the infinite area comes into play with this asymptote. We're stopping at a finite value here. So even though the function might continue on, I don't really care about the area out to infinity. We care about this area that's approaching this asymptote. So it's almost kind of turned sideways from our previous examples. And so we want to know, is the area finite? And we approach it the exact same way we did the last ones. We need to just plug in a dummy variable for our sort of problem point. And so what we want to do is we want to have the limit as, let's say, t goes to 2. The only point we got to remember now is, well, which way are we approaching this limit? Since I'm starting above and going the area to the left, we want to approach 2 to the left on the function. And we've got our t down there for that 2. And we've got our function. Our integral of this, so I'll go through all the steps for you guys. This is a u sub. It seemed like most people were pretty comfortable with this. We make our u as square root of x minus 2. Then du is 1/2 or 1 over 2 square root of x minus 2 dx. So in other words, 2 du is 1 over square root of x minus 2 dx. Ones with square roots of u sub can be a little tricky because we don't want to replace this with u. We actually just want to replace the entire thing with 2 du. So we still have our limit. Of course, these bounds were for x. And I just started writing that again. Sorry about that. Our substitution we make is just du. I was just getting distracted with the limit. Limit as 2t goes to the left. You can fill that in if you want. Or you don't have to. So again, you would approach this the same way you would if you want to find your limits. So if you want to plug in the upper limit for x, so this guy here would be square root of 3. If you want to fill in that box. The lower limit, even though it's a t, it would be u is square root of t minus 2. So this is why I'm just going to do it the other way. I'm going to leave the boxes as kind of just blank for now. I'm going to back substitute for my x's, and then I'm going to plug in the values we need. Just because with a t there, the box would be square root of t minus 2, and we'd still have a limit there, and it would just be a little messy, a little pedantic to write all that out still. So of course, the integral of du is just going to give me a u evaluated at wherever we need for u, but of course we're going to back substitute to square root of x minus 1, and I didn't give my space to write, so we got to write the limits in there still. So limit t is still going to 2 from the left, and we've got square root of x minus 2, and our original x bounds were t and 5. And of course, and we just plug everything in. So our 5, not a problem, square root of 3. And then we've got minus square root of t minus 2. And now what happens when we take this limit? Well, the limit as t goes to 2, first thing we do when we compute a limit is plug in the value, whether it's a right hand, left hand, or just a general limit. When I plug in 2 there, what do we get? Just 0, right? So no L'Hopital's rule, no indeterminate forms there. Since we get a finite number, that is what it is, and that's our answer. And that one's going to be convergent.
Why wasn't it the limit of the integral of 2 du? Why was it just du?
Did I forget that too? Yep, I did. Thank you for that. So 2, 2. Of course, we got 2's there. So we got 2 square root of 3 as our answer. Yeah. Anything else? Any other mistakes that I made?
I don't really get why it's the left-hand limit rather than the right. Just looking at the graph, maybe I'm just not remembering Calc 1 right. But
yeah, so remember, it's wherever the function is approaching. So since we can kind of think of this integral, if you want to think of it as like splitting it up in the middle somewhere, as like an integral from, let's say this is our t value, as like t to 5, and then t, we want to squeeze t to the left, is really what we want to do. So since we're starting at some point, we have to start to the right, and then we are approaching to the left. And so that's really what the minus sign means, is which direction we're going. Minus means we're approaching the negative values. Or am I talking about that wrong? No, that's right.
I always thought it was like if it's coming
Wait.
from the right side, you're approaching from the right. And
No, I think you are right. Okay, sorry. I'm forgetting my Calc 1. I'm like dyslexic this morning. Yeah, 2 from the right, since we're approaching from the right. Yes. Thank you for that. Yeah, since we are approaching from the right, we want the plot positive because we are beyond slightly bigger values of 2. Right. Thank you. So approaching 2 from the right. Didn't change any of the math, though. One of those kind of technical notation things. Sorry, brain flub there for me. Okay, so we got about 15 minutes. I'm going to write down the general rule for these guys since we're going to talk about comparisons. It's going to be the opposite of what it is for limits to infinity. So I kind of want you to get that kind of ingrained in your head, and we'll see this quite a few times. So let's recap our limit from a to infinity of 1 over x to the p. If I am integrating out to infinity, it will converge if p is bigger than 1, and it will diverge p less than or equal to 1. The opposite happens if we are integrating to the asymptote. So this was integrating out to infinity, to its right tail. If we are integrating toward its asymptote, it's going to diverge for p bigger or equal to 1 and converge p strictly less than 1. So just as we saw with this last one, it was a slightly different function because I changed it. by a shift. But that minus 2, all we did was shift 1 over square root x. We just shifted that to the right. And we saw it converged. It's a finite area around this asymptote. And so that's going to hold for any fractional power. And of course, we want in general for all of these, our p is bigger than 0. So when p is between 0 and 1, it's a fraction. It will converge around that asymptote. It will diverge if I integrate out to infinity. Notice, though, that this case when p is equal to 1, neither works, right? P equals 1, it's going to diverge in either situation because we're going to get that natural log as the antiderivative, which will blow up both at infinity and at 0. Okay, so let's just see some more examples and try to get through a couple of these real quick of just how to do some of these. We've got an integral from 0 to pi over 2 of secant x dx. Why is this improper? So secant is just 1 over cosine x dx, and cosine of pi over 2 is 0. So we can't divide by that. In other words, secant is going to have an asymptote at pi over 2. So it's going to be an improper integral around pi over 2. So we can set up our limit as t goes to infinity, or t goes to pi over 2, 0 to t. Of secant x dx. And then how do we integrate secant of x? Have you guys done this one yet? Has this shown up on any homeworks?
I think it has, isn't it tangent secant?
No, it should be like natural. It's something like natural log of secant plus something else. You need integration by parts, right? So we can't integrate this outright. It's 1 over cosine. I can't do a u sub here because it's not going to be nice. We have to do integration by parts. And unfortunately, I don't know if it's a pretty integration by parts. It might take a little work. Let's try to get through it real quick. So we've got our u is secant x dx, or secant of x. Because I don't know how to integrate secant, I can take its derivative and get secant tangent x. And then we've got our dv is just dx, and then v is x. Yeah, so maybe we'll get a secant tangent. I forget all these trig integrals. You kind of have to just go through them again. So we've got the limit as t goes to pi over 2 of, we've got our uv minus the integral of v du x times secant x tangent x. And we've still got to evaluate this from 0 to t. And then we need to integrate this guy again. And it doesn't look like we can integrate that guy. So what's going to be the problem with trying to integrate this guy? I need to use integration by parts again, yeah?
Yeah, and you still have secant.
But we have the secant tangent. So I would have to integrate that, and that would be our v. So let's go through it. The problem with integrating this guy is I don't want to take a derivative of this guy because we'll be going backwards. I want to integrate this guy and then take a derivative of this guy. And so if we do that, we're kind of just going to be spinning our wheels. Everyone kind of see what I mean by that? Because I made my du as this in the previous step, if I now make this guy my dv and then integrate it, we're kind of going backwards. And essentially we'll just be getting back to something that where we started. We're kind of just going to be going around in circles. So I'm just going to say, I'll check this later.
Can't you multiply secant x by secant plus tangent if you're trying to do the integral of secant?
Is that the trick? You
Yeah, I
multiply
think-
by like secant plus tangent over itself?
Yeah, I think that's what you do, and then you sub you do a u sub of secant plus tangent.
And you do a u sub. Yeah, we'll talk about that later. That's one of the ones where you've got to remember that fancy trick or something.
Yeah, it's
So
weird.
if you don't know it off the top of your head of how to do the fancy trick to integrate that, it's going to be hard to do. I can work that out later and show that you guys. But I mean, the key thing is just to recognize, one, when are things improper. We can do that integral later. I want to get through a couple more examples. Since we only got about 5 minutes. So one that should work out nicely with integration by parts is natural log of x, which I think you guys have done. We have our u as our natural log of x. Our du is 1 over x dx. Our dv was dx. And our v is then x. So when we integrate, we will get x natural log of x minus the integral of x over x. And of course, we still need to plug in our bounds. And so we get x natural log of x minus x. So hopefully everyone's seen that integral before. Sorry, that should be a 1 there. The problem is the t, right? So natural log has an asymptote at 0. And so we need to make that a limit problem. So I plug in a t for 0. When we plug that in, what do we get? So we plug in the 1, and we get the limit as t goes to 0 from the right. When I plug in 1, natural log of 1 is 0. And then I plug in my t to that function. And when I plug in my limit, we'll have -1 minus another 0 times minus infinity, and then minus is 0. And so this guy was our problem. And so that's what we got to consider. We need to do L'Hopital's rule again. And now this one's a little tricky. It's a 0 times infinity. So which one do we want to force in the denominator? You got to think ahead a little bit. Either might work. I would say natural logs are a little complicated. I don't want to mess with this natural log. Because if I have that 1 over natural log in the denominator, taking a derivative of 1 over natural log is going to be a pain. It's not like that exponential function where it was just a matter of changing the sign on the exponent. So we kind of have to force this t into a denominator as 1 over t. And now, of course, when I plug in 0, we will get infinity over infinity. Doing L'Hopital's rule, we get the limit as t goes to 0, 1 over t divided by the derivative of 1 over t is minus 1 over t squared. We do some algebra. So I just move the minus sign out front, multiply by the reciprocal of the denominator. So we get limit as t goes to 0 of just minus t, which equals 0. So this is our limit here. And so we just get 0 for this guy. This will approach 0. And so what is our solution? Is we had a negative 1 minus 0 minus 0 equals negative 1. So it converges. All right, so we're about out of time. We can start tomorrow with this guy. Just a little bit harder than the other ones. No, sorry. Here, I wanted that to be a +6. Yeah. So you can kind of think about, well, why is this guy improper? It's a little more hidden now. You got to factor the denominator, figure out where the zeros are and whatnot, where this function is going to blow up and have asymptotes. The other thing that might happen is sometimes there is an asymptote in between the two bounds. So we'll talk about how to deal with that. You really just have to split it up into 2 different integrals to deal with it. All right. Any other questions? So all in class today. Let me go ahead and stop the recording now. Feel free to stick around if you have any other questions.